Great, thank you, Carrie. Thank you for inviting me to speak. So yeah, I'm going to talk about energy and economic development. So if you're interested in biophysical economics, this is probably a familiar topic, but what may not be familiar is the angle that I'm going to take. So I'm going to focus on hierarchy and how hierarchy relates to economic development and consuming more energy. So energy and the economy. How does energy relate to the human economy? This is an old question, and in some sense we know the answer, right, from thermodynamics. Energy is fundamental to all non-equilibrium systems, which is the economy, which is ourselves, humans, any living system really, is sustained by flows of energy. So kind of from first principles of thermodynamics, we know that energy is the basis of the economy. But where we go from there, though, is kind of an open question. Now, often the focus is on GDP and how that relates to energy, and this is taken to be kind of an input-output relation. So we've got an energy input, and that energy flows through the economy, helps us build things, deliver services, and then we measure this output of goods and services with GDP. And of course, there's a very strong correlation between energy and GDP, which has been known for decades, and it's important. But I'm today going to focus on something that's less well known. I'm going to take a totally different angle on the role of energy in society. And I'm going to actually focus on culture, very broadly construed. So rather than inputs and outputs, energy inputs, GDP outputs, I'm going to focus on how changes in energy consumption relate to changes in culture. So really this is kind of two sides of the economy. You can think of it, energy as the biophysical side, a measure of the biophysical scale of the economy, if you like, or energy throughput. So it's a biophysical side, and as that biophysical side changes, there are obviously cultural changes, simple social changes in the structure of our society. And of course there are many ways that society changes. But I'm going to focus on one dimension of this social change, which is hierarchy. So I'm going to show you a bunch of evidence and argue that it suggests that societies become more hierarchical as they consume more energy. So I'm going to do this in three sections, so 3 lines of evidence to make this argument for hierarchy. First, I'm going to show you evidence that suggesting that as energy use increases, institutions become larger. Institutions, firms and governments become larger. Second line of evidence, as we consume more energy, we actually accumulate managers, which is kind of interesting. So I'm going to go through that evidence, and then I'm going to synthesize it all using a model and argue that all of this suggests that as we consume more energy, society becomes more hierarchical. So let's start with institutions. Excuse me. So we all live and work in institutions. Unless you're self-employed, you work in a firm probably, or maybe you work for government. So we're all familiar with the workings of institutions, but what you may not know is that their size has a trend, which is towards larger institutions, and that trend correlates with consuming more energy. So I'm going to start off with evidence in the United States, mostly because in the US, we can go back a century or more and look at the trends. So, as the U.S. has consumed more energy per person, firms have tended to get larger on average and across the whole distribution. So let's start with the average trend. Now first, here is energy use. So this is energy use per capita in the United States, going back to, I think, 1890 here. And I've labeled it on the right axis here because I'm going to compare it to some other stuff in a second. So what's important about this trend? Well, basically from 1880, 1890 till 1970, there was consistent growth in energy use, and then there was a plateau. And you maybe know why this happened. Around 1970, there was an oil crisis, a global oil crisis, and also U.S. oil production peaked at that time. So I'm not going to be too concerned with the causes here, but just notice that there's a plateau in energy use in 1970, which is interesting and I think important. Now, what I'm interested in, though, is how this energy consumption relates to firm size. So I'm going to show you firm size now, and that is the blue line here. So this blue line is the average size of firm in the United States, and it's measured in terms of the number of employees. So back in 1880, the average firm had about 3 employees, so fairly small. And that increased steadily throughout the 20th century, and today we're at about an average firm size of 9 employees. But what's interesting, at least for me, is this very tight correlation between the average firm size and energy use per person. It's extremely tight until about 2000, and you can see here that the correlation starts to break down. I'm not going to focus on this breakdown. I'm not exactly sure why it's happening, but what I'm more interested in this talk is the overall correlation, which was very tight for a century or more. So that's firm size. Correlates very strongly with energy use. We can look at the same relation from a different angle. So we can look at self-employment. These would be the smallest firms. If you're self-employed, you work in a firm with just yourself, so one person. So we can look at the self-employment rate, and that actually tends to decline as energy use increases. So again, here's U.S. energy use per capita over the last century and a bit. And now the blue is showing you the self-employment rate. Notice, though, that the scale here on the left for self-employment is reversed. I've just done that to show you the correlation. So there's a very strong correlation between the self-employment rate and energy use per person, but it's a negative correlation. So as energy use increases, the self-employment rate is declining. So back in 1900, the self-employment rate was about 35%, and it declined steadily, but then plateaued at around 10% today. So, and that's not particularly hard to understand, because a lot of what's driving this is the move to cities. So people are moving out of rural areas where they would be self-employed farmers, and they're moving to cities where they are working for bigger companies. But what is kind of not common knowledge is that this is tightly correlated with energy use per person. Okay, we can look at still another angle to this trend, which is employment concentration. So what I mean by that is employment concentration in big companies. So think Walmart, Amazon, Ford, General Electric, blue chip companies. More and more people tend to work for these large companies as energy use increases. So again, here's energy use per person in the United States. And here is the employment share in blue. Blue is the employment share of the largest 200 firms. So again, a very tight correlation with energy use per person. Now, unfortunately, I can only go back to about 1950 with this data, so we don't know what happened before then, but after 1950, pretty tight correlation between this employment concentration for large firms and energy use per person. Still one more way to look at this trend is that government tends to get bigger too as energy use increases. So Here's the last time I'll show you this energy use chart. Um, here's energy use per person in the United States, and here is the employment share of government, U.S. government. So this is all levels of government, federal, state, municipal, as a share of total employment. The dotted line here is World War II, so you know, with the war and many people being drafted, huge portion of society was working for the government. I haven't included that in the regression here, but still, what's interesting is that we tend to think of government size as being driven by politics, right? Here in the 1960s is the peak, other than World War II, peak in the relative size of government. That would be the Kennedy years, the space race. And then in the Reagan years, pretty steep decline, and we've never really reached the peak again. So that's commonly framed in terms of politics, but what's most people don't know is that this also relates to energy, right? So at the same time that government size peaked, energy use peaked as well. So I'm going to try to draw the connection and argue that this is ultimately about hierarchy. But before I get to hierarchy, I'm going to extend the evidence. So what we see in the United States, all these trends between institution size and energy use, all those trends generalize internationally, so across and within all the countries. So let's have a look at this evidence. So again, let's go back to average firm size. So as societies consume more energy, firms tend to get larger on average. Here's the international trend. So each point here is a country. This is Qatar up here. This is Bangladesh down here. On the bottom axis, horizontal axis, is energy use per person. Note that it's a logarithmic scale. And then on the vertical axis is the average size of firms in each country. And again, that's a logarithmic scale too. So a country like Qatar uses massive amounts of energy. That's partially because it's got a huge energy sector itself, right? They're drilling for a lot of oil, but also they have a fairly lavish lifestyle. It's a very rich country. So enormous energy use and also very, very large firms in Qatar, whereas Bangladesh uses very little energy and has very small firms on average. And then the trend, we can see the trend everywhere in between. So that's average firm size. We can also then go back and look at self-employment. So as we consume more energy, fewer people are self-employed. Here's the international trend. So each squiggly line here is the path through time of a country, and the dot would be just one observation. So when there's not enough data to show the path through time. So again, energy use on the bottom scale, here energy use per person with the log scale. And now the vertical scale is showing the employment share, the self-employment rate. So up here, in countries that are use very little energy, almost everybody is self-employed. And again, this is not hard to understand. These are agrarian societies mostly, or were agrarian societies at the beginning of this data. And so most people are working on farms, living on farms, and they would be self-employed, right? Very few people, there would be no agribusiness at this point. So if you're working on a farm, you're self-employed. And as people move to the cities, that self-employment rate declines as energy use increases. And then we get down here, I think this is Qatar, using enormous amounts of energy, and about 1% of the population is self-employed. So almost nobody. Sure. Yeah, so the question is about the gig economy. This data on this chart is about 4 years old. So this question about the gig economy, I'll just go back to the US because that's often where people discuss this explosion of the gig economy. So probably my data set, there was still talk in the mid 2000s about the self-employment revolution, and the data really never supported that. Now I would have to extend this data up to 2020 to kind of see the effects of maybe Uber and all this stuff. It would be interesting to see what happens, but I'm only guessing, but I would say that this trend is probably exaggerated. Certainly Uber and all these gig economy or gig companies have changed the model on paper, but I'm not sure how much of a trend this is in the entire economy. So I can only speculate because this data only goes up to about 2012, I think. But certainly I wouldn't expect it to change this this trend here. I mean, this is like a century-long trend across all the countries. So any kind of shift on here would be just minuscule if it came from a gig economy. So hopefully that answers your question. Ultimately, the gig economy is something that we need to study in the future, but I don't think it affects the findings here that much. I was talking about employment concentration. So again, we see this move towards people being employed by larger and larger corporations. So this is the employment share of the top 25 corporations in each country. So each line here is a country. This is Bangladesh down here. And then on the horizontal axis is energy use per person. And then the vertical axis is the employment share of these 25 corporations. So we have an enormous spread, right? In Bangladesh, something like 0.1% of the population is working in these 25 big companies. And whereas up here, I think this is Singapore, almost everybody is working in the 25 largest companies. And this correlation, what kind of correlates with this trend is energy use, right? So more energy means more people working in the largest corporations. And then we can go one step further and look at the size of government. As energy use increases, we get more government, or at least more people working in government. Here's the trend across countries. So each line here is the path through time of a country. Energy use per capita on the horizontal axis, and then the government share of employment on the vertical axis. And then the black line here is the smoothed trend. So you can see that it's not linear, right? Government tends to grow very rapidly with a kind of initial development, and then it plateaus over here. And then there are these outliers here, which you can maybe imagine which countries these are, and I'm going to talk about them in 1 second. I think there's an obvious question here, especially when we're talking about government, is what about politics? Politics obviously affect the size of government. So maybe they completely explain this trend. Maybe everything that we see here, there is a correlation with energy, but maybe it all just comes down to political preferences. So that's something we can test. Here's a way to test it. Here's the same chart, government size versus energy use, but now I differentiate between political regimes. So the red countries have had a communist government or have one now, whereas the blue countries have never had a communist regime. Now, clear difference, right? Countries with communist governments have a larger employment share of government, as we would expect, right, with state planning. And just to point out something that you can see in this chart, you can actually see the collapse of the Soviet Union in action. So these countries up here are Soviet bloc states. This is Estonia, Ukraine, Belarus, Armenia, Moldova. These are all countries that weren't actually countries until the Soviet Union collapsed. And the data here actually starts in 1990, right when the Soviet Union disintegrated. These countries started out with 80–90% government employment and then rapidly collapsed, right? The economy collapsed, the government collapsed, and so as a result, energy use collapsed, and the employment share of government collapsed down to what we would see in other non-communist countries. So that's very interesting. But what I want to point out here is that although we can tell that government size is affected by politics, there's something that is unaffected by politics, right? Which is the overall trend. Yeah, politics, communist politics, seem to shift up the size of government, which we can see in this inset plot. And in the inset plot, I'm plotting just the smoothed trend in all of the data, right? So the blue here is the smooth trend in all the non-communist countries, and the red is the smooth trend in the communist countries. So clearly politics affect the size of government. Communist politics push up the government size, but what we can't explain solely by looking at politics is the fact that still government tends to get larger as energy use increases in both types of countries. And I think that's unexpected. So we want to understand what's going on there. So I'm going to try to explain that. But before I do, let's review. No, I'm getting ahead of myself. Let's widen the data. So we've looked at snapshots of the size of firms. We looked at the average firm size. We looked at self-employment, employment share of large firms. These are all snapshots of a wider phenomena, which is the size distribution of firms. So I want to show you the size distribution of firms and show you how it changes with energy use. So this is the size distribution of firms in the United States. So this is a histogram, but maybe you haven't seen a histogram plotted this way. So let me break down what's going on here. So on the horizontal axis, we have firm size, measured in terms of the number of employees. So we start here with a firm with one member, and then this is a log scale, so 10, 100, 1,000 members, all the way up to firms that are larger than 10,000 members. On the vertical axis is the frequency of each size of firm, and it's grouped or binned into various sizes, and the bin sizes you can see are different. That's just the way the data comes. So each step here is a different bin. So the takeaway, or the simple takeaway, is that there are many, many, many small firms, right? A mom and pop shop on Main Street, many, many of those, versus very, very few large firms. There's very few Walmarts and Amazons. But those large firms are extremely large. And then everything in between. Now, what's important here is that this is approximately a straight line. And when you have a histogram that's a straight line on a log scale, so log scale here and log scale there, the double log scale. When you have a histogram that's a straight line on the double log scale, that means you're dealing with roughly a power law. So the size distribution of firms roughly follows a power law, which is important. So this is just the snapshot, but now I'm going to show you how this distribution changes with energy. And to do that, I'm going to return to the countries of the world. So these are all the countries of the world for which I can get average firm size data. And I plotted average firm size here against energy use per person. But this time, I have differentiated, I've grouped countries by energy use per capita. So there's 4 groups here, which I've shown by color. And what I'm going to do is take these groups of countries and plot their size distribution of firms. And that is on the inset panel here. So this is a histogram, just like we saw here. It's a histogram for the size distribution of firms, but this time it's across countries grouped by energy. So when energy use is in lowest here for these red countries, the size distribution of firms looks like this. And as you can see, as energy use increases, what's happening here is that the slope of my line is changing. So the tail of the firm size distribution is getting fatter. What remains kind of constant is that the vast majority of firms are small. So in every country, regardless of how much energy it consumes, most firms are small. What is changing, where all the action is here up in the largest firms. They're becoming much, much more common. So what's nice about this trend is that it's actually very, very simple to model. We can model it as a change in a power law distribution. So just to summarize, as energy use increases, the tail of the firm size distribution gets fatter. Okay, so to summarize, as societies consume more energy, institutions tend to get larger, and they do so in a very predictable fashion, right? The tail of the firm size distribution gets fatter. So let's move on now to the second line of evidence, which is that as societies consume more energy, they accumulate managers. So what I'm going to do is count managers. Just like I counted the number of people who worked in government, I'm going to count the number of people who are employed as managers. Here's what the international data looks like. So each squiggly line here is the path through time of a country, energy use per person on the horizontal axis, and the management share of employment on the vertical axis. And again, log scales here on both axes. So a country like Bangladesh uses very little energy and has very few managers. Something like, when the data starts, about 0.5% of the population works in management. Whereas a country like the United States up here, way more managers, an order of magnitude more managers. About 10% of the population are managers. What's important, though, is the trend across all the countries, which is this black line here is the smooth trend. And again, it's nonlinear. It's like government. We have this very fast growth of managers with initial development, and then the management share of employment plateaus. And I'm going to try to explain this using hierarchy. But before we get there, kind of obvious question, maybe this, like government, is affected by politics, right? It could be that politics are shifting the number of managers up and down. So let's have a look at that. Here's a similar plot. So I've taken this data on managers versus energy use, and now differentiated by political regime. So I've got communist countries in red, or former communist countries, and non-communist countries in blue. And you can see that there's really no difference. They're all kind of a hodgepodge there. No clear distinction like we saw with government. And we can confirm that by looking at the smooth trend, which is on this inset plot. So the blue line is the non-communist countries, the smooth trend, and the red line is communist, and there's no difference, certainly no statistical difference. So we have this very clear trend towards more managers with more energy, and it seems to have nothing to do with politics, at least a very crude measure of politics. Okay, so that is managers. More energy, we accumulate more managers. So I think that this data is interesting on its own, but I'm going to go a step further and try to unify it in terms of a broader trend, which is the growth of hierarchy with energy use. So the way that I'm going to do that is to use a model. I would love to be able to show you direct data for the growth of hierarchy, but I can't do that because direct data doesn't exist. So I'm going to use instead a model and kind of work backwards to try to explain the evidence for the growth of managers and institution size. So here's a very simple model of a single hierarchy where we have somebody at the top, probably a CEO if this is a firm, and then within the company we have a chain of command, which is these black lines. So you're probably all familiar with this structure if you work unless you're self-employed. So you either are the boss or you have a boss. And I'm going to try to use this simple model of hierarchy to explain some of the data that we saw. This model has a single parameter, which we call the span of control. And the span of control is the number of subordinates per superior. So here's what that looks like. When we change the span of control, we change the shape of the hierarchy. So when the span of control is large, like over here where there are, each superior here has 5 subordinates, and that gives you a flat hierarchy. Whereas if the span of control is steep, like the one on the right, so this hierarchy has a span of control 2, so each subordinate or each superior has 2 subordinates. We get a steeper hierarchy, and by that I just mean that there are more hierarchical ranks. So in this model, the span of control affects the shape of the hierarchy. Let's go one step further and try to model the number of managers in a hierarchy. So here's a very simple model of managers. We assume that everybody at the top of a hierarchy is a manager and everybody at the bottom is not a manager. So the rationale here is that if you're at the bottom hierarchical rank, you're what we call a shop floor worker, which is a kind of an antiquated term, but it means somebody who's literally on the shop floor. So in factories, they would have been building stuff. Now in offices, I don't know what you're doing, but that's the term kind of still in use today. In the second rank, you're what we would call a working supervisor. So these are people who still do some work in building stuff, maybe, or providing services, but they also manage people. So they are working supervisors. And then everybody above this in the hierarchy is a manager. So let's see what this model tells us about the number of managers in a hierarchy. And it tells us that as the hierarchy grows larger, there are more managers. So here's what it looks like. We're going to count the management share of employment as a hierarchy increases. So we start with one person. Clearly, this is not really a hierarchy, and there are no managers here. As the hierarchy grows, we have 3 people here in this hierarchy, but still no managers because we haven't crossed that threshold. But as we start to increase the size of the hierarchy, we accumulate managers. So now 14% managers as the hierarchy gets larger, 20% managers, 23% managers, and we could keep going. But actually, we're going to get a plateau here. So even if we went to a firm or a hierarchy that had thousands and thousands of people, we wouldn't get much above this 23%. In fact, we would peak at, reach a plateau at 25%, which is a feature of hierarchy, right? In the limit that everybody worked for a single hierarchy, there would still be only 25% managers in this model of hierarchy. And of course that is affected by the span of control, but this is just an example. So we can generalize this into a model of how the hierarchical structure of society changes with energy use, and I call this the energy hierarchy model. And I'm not going to go through the math behind it because it's a little bit complicated, but I'm going to try to give you a picture for what this model looks like, just so you can get some intuition for what's going on here. So these are the assumptions behind the model. So firms are hierarchically organized. Firms get larger as energy use increases, and they do it in the way that I showed you with the empirical data. So the size distribution of firms changes, and the firm size tail gets fatter. And finally, managers, we model managers as everybody above rank 2. So those are the assumptions. Here's what the model looks like. I'm going to show you the model visualized as a landscape, a firm landscape. So this is what I mean. So here we have a landscape of firms. Each pyramid is a firm. So the larger the pyramid, the more people work in the firm. So you can see that there's kind of this sea of small firms, even just self-employed people. And amidst this sea, there's kind of these enormous firms that live in the sea of small firms. So that this is a power law. This is a size distribution of firms. It follows a power law. Now what's interesting though, what I'm going to focus on is the number of managers. So at the top of every firm are managers, and that's the red here, and at the bottom are non-managers. And we can measure the management share of employment, and we can see how this changes as we change the size distribution of firms and energy use. So I'm going to plot this change up on the inset chart here, which shows my model of energy use per capita versus the management share of employment. So in this landscape now, here is a very different society with almost no hierarchy, right? There's almost no large firms. The average firm size here is just above 1. So you can see a few managers, little red dots here interspersed among the non-managers, but it's only about 0.001% of the population. So in this model, based on the firm size, I peg energy use very low, 5 gigajoules per person per year, and almost no managers. As we ramp up firm size, though, very quickly the number of managers increases. So now you can see a lot more red here. And so the number of managers has increased by an order of magnitude, 2 orders of magnitude actually, and yet energy use hasn't changed much. So we get this very steep increase in the number of managers, and remember this is from the growth of hierarchy. Let's keep going. Now you can start to see some firms, larger firms sprouting here, and we get again more managers. We're up to 1% of the population are managers, but really we've only doubled the energy use. We've gone from 5 gigajoules per person to 10 gigajoules. So we're still at very low levels of energy use. We can keep ramping it up, so now we see even more large firms, more managers. Keep going, but now you can see energy use is increasing very rapidly, but the number of managers has plateaued, and that's a function of hierarchy. If we keep going here, we've got this giant firm, tens of thousands, maybe even hundreds of thousands of employees, but still probably only about, in this model, 10% of its the workforce are in management. So the location of this plateau depends on some of the parameters in the model, specifically the span of control. But what's interesting, let's just back it up, fast forward it quickly, is the way this trend works. So as hierarchy increases, as firms get larger, we get this non-linear trend in managers, which is interesting. Models are always interesting, but what really matters is if this explains or is consistent with the empirical data. So let's have a look. So just to remind you, this is the empirical data for the way that the management share of employment increases with energy use. And this is the model result. So I've just, for simplicity, plotted all the empirical data now as black dots, and the rainbow here is the model. So you can kind of eyeball it and say, yeah, the model looks pretty consistent with the empirical data. Just briefly, I'll tell you what the color means. That's the span of control. So I told you how the span of control affects the shape of a hierarchy. So when the span of control is low, there are a lot of managers, versus when the span of control is high, we get a flat hierarchy with very few managers. So that's the spectrum of the model, and then here's the best fit one. So now I've plotted the blue line here is the smooth trend in all the empirical data, and the red line is the smooth trend in the model. And it's a very tight fit, other than a few points at the ends where there's actually a lot of uncertainty in the empirical data itself. So I think this model of hierarchy, this energy hierarchy model, nicely explains the growth of managers with energy use. So just to remind you of the pillars of my talk, which is that energy use is associated with larger institutions. There are more managers with more energy, and I think ultimately, if we synthesize all this data into a model, what it comes down to is that hierarchy is growing with energy use. And that, of course, raises many, many questions. If hierarchy is growing with energy use, then the question is why? And I wish I could give you a definitive answer, but I can't. I'm in the early stages of research on this, and we still really have no idea why this is going on. What I can tell you, though, is that I doubt that economic theory, mainstream economic theory, is really sufficient for explaining this. Certainly not neoclassical economics. There's nothing in neoclassical economics about why hierarchy should be important. In fact, mainstream economic theory is about the exact opposite, why the free market should be the best. But clearly we're not using the free market here. We're using hierarchy. We're using command structures inside these large firms. So what do I think is going on? Well, I think evolutionary theory gives us a much better explanation. And by that, I think there are two promising sides to this. One is maximum power and one is group selection. So just briefly, maximum power is this idea popularized by Howard Odum that evolution tends towards maximizing power consumption, which is energy per unit of time. So ecosystems evolve towards consuming more energy per unit of time, and the same with individual organisms. So certainly human evolution tends to support this maximum power principle. We're consuming more and more energy. Now the flip side of it is, why are we using hierarchy? And I personally think we should use something called group selection to explain that. So group selection is the idea that you can have many levels of natural selection, gene level, individual level, and group selection is the idea that it's actually groups that are competing. And I think this is certainly true for humans, right? We compete as groups, definitely during warfare, which is the most intense type of competition. And I think the advantage of hierarchy is that it facilitates larger, more cohesive groups. So just kind of briefly to sketch out this idea, think about the way weapons have evolved and how this relates to energy, right? Think about the amount of energy that goes into building this spearhead and how much energy it delivers versus how much energy is required to build this aircraft carrier and how much destructive power it delivers, right? That's maximum power. In any kind of warfare, this is going to win. So that's the energy side of it. Here's the hierarchy side of it, right? Militaries from the beginning were probably one of the first forms of hierarchical organization, but they've become just absolutely massive. So here's kind of what we imagine to be the baseline form of human warfare, very loose, small bands of people, not much hierarchy, versus over here, this is actually the Russian military celebrating World War II victory, I think, in 2015. So we've got tens of thousands of soldiers here, very tight hierarchy with a command structure from the top down. And imagine no matter the weapons involved, when a massive army with a command structure goes to war with a small, tiny army over here, who's going to win? Well, that's the idea of group selection, where large hierarchical groups beat out small non-hierarchical groups. Of course, this is mostly just speculating, but ultimately when it comes to this trend between hierarchy and energy, there's many open questions, and so perhaps we will discuss these shortly. If you're interested in my writing and my research, I do write about it on economics from the top down, and I do my best to write in a way that is not academic. So I write for a popular audience. So thank you for having me to the symposium. I look forward to your questions.